Hi, my name is Keith Reiser. I'm here with Mitch, Steven, Aaron, Leo, John, and Michael, and we are Psyche 2 Electric Boogaloo, the follow-up to the Psyche mission led by Arizona State University and NASA's Jet Propulsion Laboratory. 16 Psyche is a large, metallic asteroid thought to be a former planetary core. It is hoped that further investigation could tell us more about planet formation, including the formation of Earth itself. Our mission, Mission Eros, is a follow-up to the original Psyche mission to investigate unanswered anomalies involving the internal composition of the asteroid. This information is vital in concluding whether or not Psyche is really a core or not. Our mission will include both an orbiter and a lander. The orbiter, named Eros, will travel to Psyche with the lander, named Hedone, and enter Psyche's orbit before releasing the lander, allowing it to travel down to the surface to conduct experiments. The primary objective for this mission is to successfully send a satellite into orbit of Psyche and land a lander module on the surface to closer examine an area of interest. Both remote Earth observations and Psyche mission data show discrepancy between surface and internal composition of 16 Psyche. Surface observations using light reflection say the asteroid is up to 90% metal, while density observations suggest it's approximately 50% metal. To determine the truth, data is needed about 16 Psyche's internal composition, called tomography. To accomplish this, the lander will deploy a seismometer on the surface, and the orbiter will project impactors into the surface to gather tomographical data. This data will then be used to gain insight into 16 Psyche's internal composition. Secondary objectives include taking images while on the surface of Psyche, conducting chemical composition tests on the surface, and comparing the data from the original Psyche mission to the data found in Mission Eros. A hidden objective includes promoting the mission, deep space flight, and the STEM fields to the general public to gain interest. The request for proposal specifies requirements for both cost and launch date. It is required that the mission does not exceed $450 million, excluding the launch vehicle, and is launched no earlier than 2032. A couple requirements set by the team say the mission must consist of a satellite orbiter and lander at the very minimum for the mission to be successfully completed, and the orbiter must be capable of receiving data from the lander and transmitting it back to the ground station on Earth. The functional requirements will be stated and discussed in each subsystem section.
Michael Swope, and my primary subsystem is power. For concept of operations, we plan to launch by 2033 with an ideal date of 2032. The cruise phase should last between 3 to 4 years. We plan on using a Mars gravity assist with the possibility of an Earth assist. The Mars assist should take place within a year from launch. Our expected arrival date at Psyche is 2037, with an ideal date of 2036 from a 2032 launch. The lander will then separate from the orbiter to land on Psyche. The total mission lifetime is approximately 5 years. There are a couple requirements for the power subsystem. The solar panels need to be able to withstand radiation and temperature changes. The solar panels will also need to produce enough energy to power the spacecraft, instruments, and electric propulsion, while also charging the batteries to prepare for eclipses. The batteries must be able to hold enough charge to supply the instruments during eclipses, with the average time without illumination lasting up to 2 hours and over 2 hours of illumination per cycle. The primary energy source will be gallium arsenide solar cells for both the lander and the orbiter. The gallium arsenide cells are more efficient and radiation resistant and can operate at greater temperature ranges than silicon cells. The solar array areas are approximately 75 square meters for the orbiter and approximately 13 meters squared for the lander. For the batteries, we will most likely use lithium-ion batteries to store the energy for the secondary power. Lithium-ion batteries are less massive and take up less volume than batteries of similar power. We still need to determine the capacity for the batteries. The batteries need to be able to supply power for up to 2 hours during eclipses. And to determine the capacity, we'll be using the time of the eclipses and the power requirements of all the instruments and the electrical thrusters.
My name is John. I'll be talking about the attitude determination and control subsystem, as well as the thermal control subsystem. The Eros orbiter has much more stringent attitude determination and control requirements, including a need for higher precision, higher redundancy, and longer duration use than the Hedone lander. It was decided that star trackers and inertial reference units will perform the primary attitude determination for the craft, with sun trackers providing some supplementation as well as solar array alignment. Reaction wheels, xenon cold gas thrusters, and thrust gimbaling are the three methods that will be used to control the attitude of the Eros orbiter. The Hedone lander also requires high precision, but requires less redundancy and much shorter duration of use. It was decided that inertial reference units are suitable for guiding the craft down to the surface, due to the fact that the landing period should take under 30 minutes, and error accumulation in inertial reference units typically reaches a dangerous level at about 45 minutes, without reference. Laser rangefinders will also be used to determine the craft's altitude, and hydrazine thrusters are the only attitude control method that will be used. Due to the fact that hydrazine is corrosive and that the exhaust will be very hot, these thrusters must be placed on the bottom, as the sides and top of the lander consist of solar panels and sensitive scientific instruments. Theoretically, roll, pitch, and yaw authority can be achieved with only 4 supplemental attitude control thrusters. However, for the sake of redundancy and better control, 4 blocks of 3 thrusters each will be used. The most important and power-intensive thermal requirements for the Eros orbiter come from the batteries, fuel, reaction wheels, and structural elements. Taking into account all of these requirements, the spacecraft body and lander body will likely need a minimum average temperature throughout the craft of roughly -10 degrees Celsius. For thermal control, batteries, fuel tanks, and perhaps even reaction wheels will need insulation. Heat-generating components, such as batteries and propulsion, will use louvers and heat pipes to reject or redirect heat throughout the craft. Coatings will also be used to promote a more uniform temperature throughout the craft and prevent hot or cold spots.
Hi, I'm Stephen Willoughby, and I'm the lead for the structure subsystem. Before any design considerations could be made, the functional requirements for the subsystem needed to be fully defined. Firstly, the spacecraft must accommodate for all mechanical loads. This includes the vibrational and acoustic loads from launch and maneuvering. The primary structures must also handle the thermal loads incurred by the power and propulsion subsystems and from solar radiation. The primary structures also need to protect the payload from micrometeoroid strikes. A coupling system needs to provide for safe attachment of the lander, Hedone, to the satellite, Eros. Looking at Hedone, the lander must provide for safe landing on Psyche and stability after landing. The primary structure must also protect the sensitive scientific instruments on board. With these requirements in mind, it was decided that the landing gear would be a non-deployable truss made from carbon fiber reinforced polymers. This material will have sufficient strength for Psyche's low gravity. The material is very light, with a density of an average of 1.6 grams per centimeter cubed. The material is more expensive than traditional aluminum and titanium alloys used for landing gear, with a raw material cost of $85 per kilogram. However, it was deemed to be worth the additional cost in order to reduce the mass of the lander.
The request for proposal specifies requirements for both cost and launch date. It is required that the mission does not exceed $450 million, excluding the launch vehicle, and is launched no earlier than 2032. A couple requirements set by the team say the mission must consist of a satellite orbiter and lander at the very minimum for the mission to be successfully completed, and the orbiter must be capable of receiving data from the lander and transmitting it back to the ground station on Earth. The functional requirements will be stated and discussed in each subsystem section. After many trade studies and deliberation sessions, it has been decided that the orbital will use an ion propulsion system consisting of 4 SPT-140 Hall thrusters containing xenon gas propellant. Calculations shown in the final report determine that the system will require approximately 2,000 kilograms of xenon, which will cost up to about $2.4 million. This system is very similar to that used in the original Psyche mission. The success of this system throughout this mission encouraged the group to follow the same path. It has also been decided that the lander will use a monopropellant propulsion system, using hydrazine as the propellant. It is estimated that approximately 75 kilograms of hydrazine will be needed, coming out to about $1,275 worth. The image you see here are some of the monopropellant thrusters manufactured by Moog. We believe that the lander will need 1 large thruster for descent and landing control, and at least 4 smaller thrusters for attitude control. After calculating the thrust needed to complete each maneuver, which includes slowing the lander down to 0 once released from the orbiter and creating enough thrust to safely reach the surface, it is believed that the Monarch 445 will suffice as the large central thruster, while the Monarch 5 or Monarch 22 will suffice as the other cluster thrusters for attitude control.
Hello, my name is Mitch Adler, and I was the lead for the communications and vehicle subsystems. Before we get started, it's important to define our requirements for the communications subsystem. So first of all, the ground control must be able to communicate with the Eros orbiter and the Hedone lander to effectively send commands and execute maneuvers. And the lander and the orbiter must also be able to relay information back to Earth. Because of the mass and power constraints of the lander, it is more beneficial to have the lander communicate with Earth by relaying through the orbiter. We will be using the deep space optical communications, which is a new technology for the orbiter. Simply because of past mass and power constraints. This optical communications technology can achieve a 50% mass reduction, 65% savings on power, and or a 20 time increase on data rate. For the launch vehicle, we have decided on Falcon 9, simply because of cost benefits. The bus that we are using, called the SSL 1300, is compatible with 5 different rockets. 2 of them are manufactured by foreign countries, which make them unviable. The Delta IV is much too heavy for the mass requirements that we have. So that leaves it down to the Atlas V and the Falcon 9. The Falcon 9 costs only $62 million, which is nearly half of Atlas's $109 million. And Atlas V has flown just 74 missions all the way up until 2017. And Falcon 9 has flown over 80 missions since 2010 when it was first created. So it seems to be a much more reliable and efficient choice.
I'm Aaron Sheffield, and my primary subsystems were ground control and command and data handling. The NASA Near-Earth Network and Space Network aren't capable of functioning at the distance of 16 Psyche, so the ground control subsystem will use the Deep Space Network. The Deep Space Network is more costly than the other 2 networks, with the price being based on a base aperture fee, a weighting depending on which satellite dishes are in use, and the number of times per week contact needs to be made with Eros. For command and data handling, the Eros and Hedone architectures are based on their unique geometry. Eros subsystems are separated, and the center is inaccessible for wiring. Because of this, Eros requires a bus architecture type. Hedone is geometrically compact with the possibility of central wiring. This allows for a centralized or federated bus architecture type to be used. Eros requirements are storage space for subsystems and recorded measurements. Eros should also maximize automation to reduce required contact from ground control. Hedone requirements are storage space for subsystem software and data measurements, with data measurement storage space being maximized.
Hi, I'm Leon Galanakis, and I'm going to be talking about the scientific instruments. So there are certain requirements that the instruments have to meet in order to achieve the mission objectives. For example, the lander Hedone must be accurately deployed at the area of interest, which was identified from the original Psyche mission. Once landed, Hedone must then be able to maintain communication with the orbiter Eros. The instruments must also be protected from the harsh environments to ensure they stay within their temperature and radiation limits. The instruments must remain fully functional for the entire mission. Redundant systems will be included so that if something fails, the mission can continue as usual. The tomographic data will be obtained using the lander Hedone, equipped with seismometers. These contain a fluid which is very sensitive to movements. The motion of the fluid then generates a current which can be associated with certain movements. Multiple of these cells are arranged in such a way to detect movement in all axes, with redundancies included. This technology has been tested on Earth and has been studied and planned for use in missions on small bodies such as asteroids. The vibrations will be created by firing impactors from the orbiter onto the surface of the asteroid, a form of active seismology. Two main types of impacts are blast impacts or cluster impacts. Cluster impacts will cover a much larger area, adding to the complexity of the seismic signals, however, will have a much lower impact energy than the blast impacts. Blast impacts also have the added bonus of creating craters, allowing the analysis of cratering behaviour and materials just below the surface of Psyche. There is still a lot to work on for the future of this mission. Professionals such as those working in industry or professors can be consulted for second opinions. Also, more work can be done in improving the estimated budget for the mission, trade studies can be further explored in more detail, and lastly, more in-depth design work will be worked on constantly throughout.